just yet, but I should have them completely graded on Friday at some time. I put on the Canvas page, it'll be done on Sunday at the latest, but sooner than later for sure.
Yeah, you're usually pretty fast.
Well, it's time. Welcome back, everyone. Looks like a small class today, but we'll still get through it. We've at least got a representative in Zoom, so welcome to the class, Casey, and also a representative in person in the classroom. So that's good enough for me to get going. And as far as the announcements go, congratulations on getting through the very first exam. I'm going to start making that my first thing I want to do on Friday is begin grading exam 1 for everyone. And I should have it complete on Friday, but if it turns out to take longer than possible, my last time I would be working on getting it completed is Sunday evening at the very, very latest. For everyone in the class, I'm going to upload under grades your exam score, as well as a PDF copy scan of your exam, even if you took it in the classroom. That way you can get your feedback a little bit sooner. Then when we come back, not on Monday, but on Wednesday, I'll be handing back the hard copies for those that took the exam in the classroom. But aside from that, we're pretty much wrapped up exam 1. Assignment 4 is going to be due today, and we're working through our chapter 14. This due date I might adjust because I'm not going to try to race through chapter 14 to get it finalized today. So if we have to come back on Wednesday after the President's Day holiday to finish chapter 14, we'll make sure to come back and do it then. The other thing to mention is pretty much this class just goes in waves. We got through wave 1, getting through week 5 with an exam. Then we'll have a holiday. We earned it, we deserve it, and normal weeks until we're getting to about here, and this is going to be the second wave. And the way you saw things get built up in Canvas, I'm just going to replicate in the same exact way. Meaning, before we even make it to this week right here, I'll have the exam content laid out, the sample exam exercises, and so on. And before you make it to this week, well, probably first thing on Monday on this week, I'll be emailing everyone instructions on scheduling your exam. So it'll be just the same rigmarole over and over again. We'll do the same thing for exam 3. And our final exam is going to be different. This one is just going to be a take-home exam. Not exactly a project, but sort of like a project. That's comprehensive with the whole course with the emphasis on statistical methods. We'll assign that one probably on Wednesday after reviewing this week here to be due probably, well, we said Thursday, so definitely due Thursday of finals week. But pretty much this is how the entire course is going to go on a week-by-week basis. This stuff that you see here on the Canvas page. Well, any questions at all, folks, to get us started today while I try to get that back to neutral? Okay, well, let's jump in. Chapter 14 is a strong emphasis on introduction to statistical methods. The main things we're trying to think about were how the central limit theorem provides us the statistical method for the confidence interval and hypothesis test, but also how to analyze top to bottom and give a strong conclusion for a confidence interval procedure and a hypothesis test procedure. Chapter 15 is going to just be additional topics about inference. But in chapter 17, we take off the introduction part here, meaning we're not going to be using the simple conditions for inferences. We'll be doing a little bit harder condition checking on each problem. But for the moment, while we have it, let's take a quick screenshot of that. In chapter 14, this is what we're going to check to see if our sample data meets the criteria for these conditions. So here's where we left off last class. We finally defined our confidence interval method, which also finally answered the question on what is the margin of error in making an estimate. So this entire interval does this. It estimates an unknown parameter mu. And in our problem here, the unknown parameter mu was, let me just zoom out for a moment, the mean, or you could say average, radioactive tissue concentration for all Pacific bluefin tuna nearby the coast of California 4 months after the 2011 meltdown. And we chose a 95% confidence interval. So that's our unknown in the problem. When we make this estimate here, the margin of error in the estimate will be Z star times sigma over the square root of the sample size n. So we already have an estimate for the unknown mu. It's right there, 10.3 becquerels per kilogram. That's the measure of radioactivity in this problem. So it estimates mu, but now we have to go further and capture the margin of error. Essentially, we'll produce the entire confidence interval and give a strong conclusion for it. Any questions at all, folks, with just kind of the warm-up so far, revisiting this problem and the parameter? Okay, in a really strong sense, this is like the hardest step right here, saying exactly what mu is. And it's a critical step because this interval up here is also worthless if we can't give a strong conclusion in practical, ordinary terms, what it really represents. But writing down the parameter mu carefully at this step really solves a lot of that work. All we need is the numbers for the lower bound and the upper bound. But even before that, it's a good idea to check conditions. So we'll do some condition checking on each one of these problems as a warm-up to what we'll be doing in chapter 17. So it says, check if the conditions are met. Here they are, just screenshotted in as a quick reference. First thing we need is a random or at least representative sample. Here it asks for a random sample itself. We need to check through the statement of the problem. We're told they do have a random sample. Now, I don't know how you randomly select Pacific bluefin tuna, so they must have had a team of ocean biologists that tell them that they are doing the right kind of process to get a nice representative sample for that particular population, because it's not an easy one to work with. So if we trust that biologists that were informing the statistics on how the sample was selected, that it was done randomly for this population, we do meet condition one. We can say the sample is random. So that's one down. At best, we want a simple random sample, but we'll take any indication that at least it's random in order to pass that condition. Second condition is the variable we measure has a perfect normal distribution. And that is a really strong assumption, and it's probably false. But we'll use the central limit theorem in chapter 17 in a more direct way to explain why it doesn't have to be perfectly normally distributed. But nonetheless, we have the sample data. Let's see how close to normal our data looks if the population really is normal. So going back into RStudio, I have the sample data imported here, but let's do just one little thought experiment before we look into the sample data. So imagine the population is exactly normally distributed, like condition 2 says. When we gathered a random sample, I'll say X gets R for a random sample, norm to say it comes from the normal distribution. And I'm not too worried about the parameters, so I'll just go with 0, 1 on this one. First, I want a sample size of 16 because that's the sample size in the study. So mean 0, standard deviation 1. And if we look at the histogram of this random sample, which is extremely nicely simulated through this R-norm sampling process, here's what it looks like. That one wouldn't be too bad. It has a very strong main peak right here, but for a sample of size 16, that would be terrific. In a different run, if we took a different random sample, that one's not too bad either. It has something weird going on here where the data is trailing off to the right slightly more, but still not too bad. That one's almost perfect. That one's kind of shocking. I'm getting really good draws on this. So let's see how bad it can get. Now it's getting weird. The skew is a little bit more substantial on this one. On the next run, even weirder still. And keep in mind, this came from the normal distribution. So this one's a little bit concerning. We have a main peak here, another main peak here, and data trailing off. This one could be a showstopper for us. This one is bimodal, two main peaks. But worse, it's very strongly left skewed. The data trails off to the left a lot after congregating here on that range, then trails off some more. This one might allow us to stop actually using this procedure. Because if our data looks too weird, we suddenly have some evidence that population wasn't actually normal. Like keep in mind when the samples are small, like we have here, lots of weird things can happen. So in a different run, we're back to something nice, and then back to something weird on the next run. This one wouldn't be that bad, but it's starting to get borderline because we might have some outliers way out here. So now thinking about what can happen with a sample at size 16, like in these data, let's put the plot for the histogram of our data. Really, we're just returning to chapter 1 of the course. I have the data imported here. Oh dear, let me remove a variable. There you go. So now it's just that data here. Instead of using the entire example 3, chapter 3, I'm just going to extract that unit and call it rad for radioactivity. So rad gets example 3, chapter 14. I had to name it that because Canvas doesn't want multiple example 3s, so I had to say in chapter 14. Select becquerels per kilogram. The histogram of the radioactivity will be just this, but let me put in some extra options. Deleting the main title, and for the horizontal title, we can call this, how about radioactivity in becquerels per kilogram. So that'd be a good description for the quantitative variable unit. So again, this is kind of just revisiting chapter 1, chapter 2 work, producing the histogram. And here's what we get. You know, it's not great, but it isn't bad either. I don't like that there's a potential bimodal situation going on with these data, but in terms of skew, it's really not that terrible. For a sample of size 16, it is very plausible that this came from a normal distribution, because keep in mind, things that come from the normal distribution can look really weird, like in these last graphs. So if we got sample data that looks like this in a sample size 16, we wouldn't be too worried about it. We can take this, put it in our document, and now for condition number 2, I would say something along these lines. The data appears bimodal due to the 2 main peaks. The major peak is between 10 and 12 becquerels per kilogram, and it does trail off more to the left. So we can say with a slight left skew. But there's no strong outliers. The skew isn't tremendous. So it's very plausible these data may have in fact came from something normally distributed. So we'll say here, it is plausible these data came from a normal distribution. So that addresses condition 2. Condition 1 was just checking the information in the problem. Condition 2, we had to look into the data and analyze it. Any questions so far with either of those conditions? Okay, as far as condition 3 goes, we don't have to mention everything verbatim as we see it, because this assumption, we don't know the population mean mu, is a total given in these kind of problems. That's the major thing we are trying to do, estimate the unknown parameter, the population mean radioactivity for this entire population of bluefin tuna. So you don't have to reiterate this part right here. No harm done if you did. But here's where it gets weird. Our method, again, is not the best method out there. We're going to clean it up in chapter 17. Our method requires we do know the population standard deviation sigma, so we have to double check. Sigma was given, and so this condition is met. We can use the procedure for the confidence interval as it is stated. So I'll say here for condition 3, since sigma equals, and I forgot already, let me scroll back, 2.95 becquerels per kilogram is given, this condition is met. So overall, we have everything we need. The random sample, the data isn't too weird, there's no strong skewness, no outliers, and we have the parameter value we're going to need for the computations coming up next. So it's a pretty short discussion. Sometimes they do get more involved, say chapter 17, then chapter 18, even more involved. So we'll spend quite a bit of time discussing the conditions, seeing how they go. Think of this as kind of a warm-up to what we're seeing later on in chapter 14. And also finally explain why we took so much time thinking about histograms for quantitative data. So now we're into the fun part, just the computational side of all of this. Any questions or comments at the moment? Okay, as far as the necessary computations go, there's a couple ways you can do this problem, pretty much as a standard math problem where you state the formula. The formula is x bar plus or minus a critical number. I think we used purple or something for that, times sigma divided by square root of n. All we need to do is find those values, drop them into the diagram, or excuse me, the document, substituting them in, and we're pretty much through this problem. I'll show you how to do it the RStudio side as well, just in case you'd like to see how that goes. It can be quite efficient. But it's good to know how to do this both ways, by hand like we're about to do, because if this was an exam 2 question now, you'd be expected to know how to do this by hand. So plugging in the values, first the sample mean, we computed, but let's put it in our syntax so we can have a paper trail in our syntax as well. So there's our data imported, the histogram above, and we can call x bar mean for rad. So there it is. X bar is handled. For Z star, we can do a table lookup for what we already put down in the notes. We're going for a 95% confidence interval, so it's 1.9600. But this is a powerful system. If you didn't want to round, you could just say C for confidence is 0.95. That's coming from right here. Make sure you put it in as a decimal number. And then once your confidence level is stated, the syntax to get Z star is Z star gets Q norm, put in 1 minus C divided by 2, lower dot tail equals false. So that's the same syntax that we visited earlier on, calculating those critical numbers. So now we've got the Z star. We're going to need sigma, so let's throw that in as well. Sigma is 2.95 in this problem. Well, we're going to need a sample size, so let's put in n. Sample size was 16 in this problem. So that's all of our information. If I run this, the major thing I wanted was Z star, but again, you could have just went up to the table and grabbed that value. To 4 decimal places, pretty standard for a critical number rounding, 1.9600. So plugging these all in, whatever else do I have? X bar is 10.31. Add and subtract 1.9600. You don't need the zeros, but that's just a kind of a reminder for me that that's a pretty accurate number we dropped in with 5 significant digits there, rounded. Next for sigma, we have the value 2.95. And we're dividing that whole thing by the square root of the sample size, 16. So plug that into a calculator and you're on your way. If this was an ordinary calculator, say you're doing this in an exam setting and this is your TI-30X2S, it just happens to look like this. All I would be doing is go 10.31 minus, I want to get the lower bound first, 1.9600 times 2.95 divide by square root 16. That gets the lower value. I'll round this. Let's take a look into the data. These have 3 significant digits. I'm not going to be picky on rounding, but I'd say it's a good call to go for 3 significant digits as well. 8.86 is less than something, which is less than, then your calculator, oftentimes you can push a certain button to bring up that last computation, flip it to positive for a plus, and there's the upper value. This one will be 11.8 becquerels per kilogram. And the thing on the inside is mu, the unknown of the entire problem. We now have an error bound for it. It's as low as 8.86 becquerels per kilogram and as high as 11.8. The sample mean itself, 10.31, is in the direct center of this interval between those two bounds because of the plus and minus action we have here. But we did it, folks. That's our very first 95% confidence interval for the whole course. Any questions at all on the computational side of it? Okay, if you're putting it in syntax like this, pretty much all you would do to get the same result is go x bar minus z star times sigma over square root n, then copy that line, do the same thing with the a plus, run the whole thing, and we get the same values coming right back. So it's kind of up to you how you'd like to calculate it. I'll put the syntax here just as an easy reference, well, maybe below the problem, if you like to do it in this way. Well, all we now need to do is give a practical interpretation. We have to involve the context. And also there's some specific guidance on exactly what we mean when we say practical interpretation. If you go to, say, assignment number 5, or this document right here, complete analysis, it gives us some guidance on what we mean whenever we see practical interpretation using the context. So we might as well pull that up. By practical interpretation, we mean one in which a layperson, someone who's never taken any statistics ever in their life, will understand. So this person may or may not have ever taken statistics or probability. That means we're returning to what we said in the original step, the statement phase. We're not going to use any specialized symbols. For example, if this problem is really, really important and you said, with confidence 0.95, 8.86 less mu less 11.8, people would think you're a robot and they would have no idea what you're talking about. We need to break down that language, pretend we're presenting this to, say, Congress or to a news station, so that everyone understands what the results really were for this study. Other advice are, we don't write any mathematical symbols whatsoever. And if there's any limitation of our conclusion, if the data started to look a little too skewed to your eyes and it's a little bit worrisome, mention that at the very end, how your conclusion could be challenged. So with that guidance there, here's what I would do for writing out any kind of practical interpretation involving a confidence interval. Go back up to where mu was, as well as the confidence level. Let's bring it down. Our practical interpretation goes like this. With 95% confidence, so we're starting off by saying what the level of confidence was for the interval. And that's really important because, once again, this didn't have a ton of precision in the interval. The margin of error is pretty wide. But if you gave, say, a 5% confidence interval, run the whole thing, suddenly it looks like you did statistics so super well because that's a precise looking interval. Extremely narrow when we drop the confidence. But we are only 5% confidence the parameter would be in that interval. So we start by being honest and saying what our level of confidence is on this procedure. So we go back to that actual values we had. After we state the confidence level, just go back up to this. We can say the mean radioactive tissue concentration. I'll say for these fish, referring to specifically the Pacific bluefin tuna, caught off the coast of California for months after the 2011 meltdown is between 8.86 and 11.8 becquerels per kilogram. So that's the interpretation of the entire confidence interval. And one comment I want to make right away is, I understand it's kind of painful to write out mu twice. And this was a longer description from you, so it was extra painful. The reason I required this to be written out once is because if you write it out once in the planning phase, I have found over the course of teaching this class well over 12 years now, people tend to do really well on this step right here. So we do have to say it again. Sorry about that. But I find writing out twice again just makes everyone a lot more accurate. In particular, once you have that under your belt, the exams are going to be a lot easier as well, getting that conclusion just right. So sorry for the redundancy. It feels kind of painful, but we'll get through it together. Other thing to keep in mind is, once you've written down the conclusion, return all the way to the very, very top. The question was, do these data provide significant statistical evidence that the mean radioactive tissue concentration is above 2 becquerels per kilogram? Well, our interval on the very lower end is 8.86. So yeah, we have overwhelmingly strong evidence for that. So we need to add that to our conclusion. This provides an overwhelming, you don't have to say overwhelming, but this time it's pretty strong evidence. So I'll say it here, overwhelmingly strong statistical evidence, the mean was above 2 becquerels per kilogram, that 4 months after the 2011 meltdown. So that's our whole conclusion. We have interpreted the confidence interval. We threw in the context every time we mentioned the unit, the fact that we're talking about the fish, and we redressed the original problem in the start of this entire analysis. Any last questions or comments at all, folks, getting through this? Okay, one thing that's a pretty easy mistake to make on this is we can't say probability, and that's kind of weird. That number mu is just some kind of finite number, and it was either in the interval or it wasn't. This is not 95% probability that mu is inside this interval. So we cannot say probability. That's kind of surprising in a way. The confidence level is a probability, but it's a probability for a very complicated event. It's the probability for the event that you took a random sample of size 16 fish, calculated your sample mean, and produced an interval that was successful, that accurately captures the true parameter. If you took a whole different simple random sample, you have an entirely different confidence interval. So the confidence level isn't the probability that mu is in the interval. It's the probability that the whole method succeeded. And if we did 100 different confidence intervals, we'll have 100 different lower and upper bounds, almost guaranteed. 5 of them won't contain the true parameter mu, but 95 of them will, if we're talking 95% confidence. Well, I have other practical kind of concept thoughts that we're going to go along with the confidence interval on the next page before we turn to hypothesis testing. But any last questions or comments at all, folks? Getting through our very first interval, first of many. Okay, so let's scroll down here. Here's the syntax if you want to do it as a RStudio kind of problem. And down below, this is a pretty tricky question. Some of these questions come back in the homework assignment as well, and some of them could be a concept question as well on exam 2. I probably wouldn't ask this many concept questions on exam, but maybe 1 or 2. I don't want to overload it with very, very tricky questions. But this is some really important context to think about because some of these are kind of surprising. It says, suppose we have computed a 95% confidence interval as an interval in interval notation in math, AB, for the parameter mu. So that's the unknown. And if we prefer the inequality form, you could say A is less than B, or rather A is less than mu first, is less than B, is that confidence interval. Just another way to visualize it. I feel like the actual interval notation mathematically sometimes is not as well conveyed as the inequality form, because the inequality form puts the unknown right in the middle. We're just forced to look at it and think about it and deal with it. So here are the tricky concept questions. True or false? If we randomly select an individual from the population, maybe bluefin tuna again, there's a 95% chance the interval that the individual is inside that interval. Let's think about that one. Anyone see if that should be true or false? The trick to this question is basically that statement right there. It's talking about randomly selecting one fish from this population, if we're thinking in the last example. But that's not what the parameter mu is. The parameter mu is the average or mean value radioactivity for all fish in that population. It says when we produce this interval, nothing at all but one single individual from the population. So this one would be false. The interval describes the population parameter mu, not an individual from the population. Deserves an exclamation mark because that's probably one of the very first misconceptions that ever comes up when we're thinking about confidence interval. For example, in the last problem, the interval that we came up with from 8.86 to 11.8, that doesn't capture a single individual with 95% confidence. It's capturing the mean of all of the fish that could be potentially caught off the coast of California 4 months after the meltdown. So that's one down. Any questions so far? Okay, now next one is just as tricky, maybe even worse in a certain sense. It says for true or false, there's a 95% chance that X bar is in the interval from A to B. Any volunteers for a guess on this one? Definitely kind of tricky when you think about it, right? Every one of these questions are nasty. So it's why we're doing them definitely right here and now, before you see them again in the homework, and potentially before you see one or two of them again coming back in an exam setting. These would be really rough ones to just jump the gun on and see as a surprise. But here's the trick to this one. It's almost silly once you kind of look into it. X bar being in AB, we can say that this is false. What made it false? It's the percent chance. There's 100% chance. And that's because the sample mean is the center of that entire interval. There is a 100% chance X bar is in AB because the interval is computed this way: X bar plus or minus the Z star times sigma over square root of n. But that implies X bar is the center because we're adding the same amount and subtracting the same amount, the margin of error, to X bar itself. That places X bar in the center. So this one is always in the interval. In fact, it's in the dead center. So 100% chance on this. Again, this one is probably the more important question right here. Part B is just a reminder, what is the interval in the very first place? How did we build it? It placed X bar in the center, was what's going on with this particular version. The next ones are maybe a little bit more on the practical side, talking about what happens if you change sample size, what happens if you change confidence levels, and we have syntax ready to go to kind of think about that. Let's go carefully on this one. It says, if the sample size were to increase, would the confidence interval become wider or narrower? But where is the sample size? It's right there in the denominator. If you make that bigger and bigger and bigger, that entire factor after the plus and minus will get smaller and smaller and smaller. As n tends towards infinity, this whole thing tends towards zero as a limit. But that's good, right? Higher sample size means narrower intervals, and that's what we try to get, more precision in our estimation. And we can definitely check that out with our syntax we wrote here. We had a pretty wide interval from 8.86 to 11.75. Suppose the sample size was 160, and check out the change. Now it goes from 9.85 to 10.76. If it was 1,600 fish, they're working really hard on this problem. Probably they need a fleet of boats because time was of the essence. 4 months after, they can't take so long that it took them months to complete this study. And now the interval is extremely narrow with such a large sample size. But that might have been totally impossible to do just on a cost basis. If you put that many boats out, maybe you're disturbing the fish in the first place, causing even more problems with random sampling. But it's good to know, within reason, we can increase our sample size and make the interval narrower. So let's say here, narrower, because the margin of error, we usually denote that by lowercase m. It's equal to the critical number z star times sigma over root n, gets smaller. All due to that n being in the denominator. And again, that's good in a way. Smaller sample sizes means narrower intervals. But part D is a major concern. This is the reason why we always report the confidence level on any analysis that we give. It's a form of being honest with the level of precision and accuracy in getting that result. It says we did a 95% confidence interval. Let's bring that back here to the normal interval. If we were to decrease the confidence level to 90, would the resulting confidence, that's not quite grammatical, let's fix that. Would the resulting confidence interval become wider or narrower? Explain. Any volunteers for an assessment on this one? Should we get wider or narrower on lower confidence? while we're thinking about that, let me tell you how I sometimes think about this problem, which kind of hurts my brain a little bit. There is a conflict of directions. Lower confidence sounds bad. So it sounds like you would get the thing that's bad, which is wider intervals. We want narrower intervals. But that's not actually true. If you drop the confidence, let's think about this, at 95% confidence, I'll just use uppercase C for confidence, Z star equals 1.9600, and at 90% confidence, Z star equals, we have it somewhere up on the table, but this is almost faster. Let's just compute it right here. Drop the confidence level to 90%. Put a new line just to output Z star so we can take a look at it. It went down to 1.6449. But where does Z star go? That's the next question in this analysis. Z star goes right here. So as confidence drops, that factor goes down and down. And if that gets smaller and smaller, we get something that is narrower. So at less confidence, we get a narrower interval. So it's sometimes, if we're being extremely unethical, cheating with statistics, we could start just like we looked at before, drop the confidence down, 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 maybe 1% confidence or 0.1% confidence. That's ridiculous. But look what happens to the interval. At that remarkably low level of confidence, our interval looks like it's just the most precise thing ever. Like we did amazing statistics. We need a raise now, but we're lying. And if we ever try to publish that, people will call us out. And now we're probably going to be in really big trouble after that. Tarnished reputations, all that kind of bad stuff. But those are the major concepts so far. And part E is just coming back to a comment we made before. Whenever we go to interpret a confidence level, we can never say with probability 0.95, or there is a probability of 95% and so on, 95% chance. We have to always say confidence level, and we'll visit that in part D just to tie that idea together. First, any questions whatsoever, folks, with any one of these concept questions at the moment? Okay, so this is the big one. It says, when we give a practical conclusion, we state the confidence level, and we must do this in the homework. Let's just make that a paper trail there. Must do this in homework and on exams when we go to give conclusions. However, we do not consider the confidence level as being the probability that the parameter mu is in AB. So that begs the question now, what does that confidence level actually represent? It's a huge event that's going on. 95% confidence is the success rate of first obtaining a random sample size n, then producing a confidence interval that's the whole x bar plus or minus z star times the sigma over root n, and then obtaining an interval that contains the unknown parameter mu. In other words, mu would be be between the lower bound with a minus and the upper bound with a plus. We won't actually know if mu is in that interval whatsoever. We have no clue. And the only way we could actually be 100% certain is we would abandon the sampling, random sampling, and we would go take a full census, better be 100% accurate, an entire census of the population, measure every single individual. And the problem that we were just looking, those fish, that would be a bad thing. If we were trying to take a census of the Pacific bluefin tuna, we've captured the entire population, and we've also wiped them out. It would probably be the assessment, because finding the meat, the radioactivity, absolutely kills the fish. So we can't even determine if mu is in our interval. All this is the success rate of producing an interval that really does contain mu, and whether it did or not, we will never know. We can never be 100% confident. That'd be the entire real number line as an interval. So that's the major reason we always say confidence level. We're not saying we know the probability mu is in that interval. That's impossible without a census. Well, we did it, folks. That's the full rundown of all the tricky concept questions that go along with confidence intervals. Any last questions or comments so far? Okay, there's two kinds of interesting styles of analysis that we're going to be looking into in this course. The confidence interval method is nice. It gives us statistical inference and an estimate of the parameter at the same time. And the next kind of question we're going to look into is hypothesis testing. When you do a course like this, it sometimes feels like hypothesis testing and confidence intervals are things that live apart. You do one or the other. It's actually not true. They go together. Oftentimes, if you do a hypothesis test, you follow up with a confidence interval estimate, but we're going to be looking at them as separate questions. I just want to give a big heads up on assignment number 5. If you're going to start this one early, here's the PDF. The thing to watch out for in assignment number 5 is you have to do the specific method to get credit on the problem. So exercise 4, I recopy these out of the book, but sometimes I change the method because I feel like maybe it works better as a confidence interval rather than a hypothesis test. We really have to do this one as a confidence interval. If you did the hypothesis test, you'll lose credit on this question, which hurts, but I'll just email you back or make a message in Canvas that says, or a message on your paper directly that says, if you redo the problem as a confidence interval, I'll accept it for full credit. So if you mix up the methods, it's kind of annoying, but you can recover that credit. This one is asking for directly a hypothesis test, so we cannot do a confidence interval on this one. But you'll know it's going to be a hypothesis test when, in the planning phase, it's asking for a null and alternative hypothesis. And likewise, you'll know the other problem is a confidence interval problem when it says just define the parameter, and they gave you a confidence level to work with. Or perhaps in some problems asked you to come up with a level of confidence. So that's one thing that gets kind of tricky in this section. There's two styles of analysis. We have to be very mindful of which kind of analysis we're giving on a problem by problem basis. But now let's turn it over to hypothesis testing. We'll talk about it a little bit. I don't think we're going to solve the very first problem just yet. But here is our early look on hypothesis testing as a method. There's lots to say about hypothesis testing. We do confidence intervals first because it's a little bit simpler to just step into the procedure and give a nice, compact, and accurate conclusion. But it feels like there's more moving parts in hypothesis testing because there really is more moving parts. Let's go through this slowly. When we say hypothesis testing, it means we have a claim that's going to be tested through a statistical test or analysis, and the claim to be tested is referred to as the null hypothesis. We'll write our null hypothesis sorry, just choosing a color here. Let me go with blue. Maybe that'll be better. We did write out our null hypothesis as just at H naught or H sub 0. There's another claim, the completing claim, the one the research team is trying to find evidence for, trying to show statistically, is referred to as the alternative hypothesis, and we write it as HA. I put it here as lowercase. I think I usually write it as uppercase, but I'm not going to be too worried about the case. That is a distraction. Let me put it as an uppercase just to match up with the notes. So the competing claim, the one, if this is your important research problem you're trying to find evidence for, is the alternative hypothesis HA. And there is some good news about hypothesis testing. It is confusing to talk about very first, but if you've ever watched court TV or if you've ever watched things like Law and Order, some kind of courtroom drama, what's going on in those courts of law is a very accurate representation of the same exact logic that we use in hypothesis testing. In a court of law, the null hypothesis, this is the claim to be tested, is that a defendant is not guilty. And in statistical analysis, we are like the prosecuting attorney, or the team of prosecutors potentially. We are finding as much evidence as possible that the defendant is in fact guilty. Instead of, say, calling witnesses and trying to convince a jury, we'll be using probabilities that we'll call p-values to come up with evidence for this claim. Well, in those courts of law, the very first thing that they do is they make an assumption. This is a critical assumption. We'll be making that assumption as well in hypothesis testing. They assume right at the very get-go, no matter how weird or implausible it might seem to the public, the defendant is not guilty. They assume the null hypothesis is in fact true right on the onset. Then they gather evidence and show that that assumption is unreasonable. We'll use probabilities to do so. And that's the competing claim we're trying to find evidence for, HA. If we do not find enough evidence, if our p-value is big rather than small, it doesn't mean we have proven H0 is true. And this is also the same in a court of law. You might have seen things on the news where someone looks just obviously guilty to you, but the prosecuting team just didn't come up with the goods. They didn't find enough evidence against this person. It did not mean at the end of the courts proved innocence. That's impossible. They never prove innocence. All they have shown is if we do not have sufficient evidence for HA, it doesn't mean we prove the defendant is not guilty. We just found a lack of evidence against that claim. So the big, strong reminder that will come back to us in the notes, really the whole course is, we do not have sufficient evidence for the alternative hypothesis. We still, let's not use the word still, we do not conclude H0 is true. So that same exact logic will carry over into our conclusions as well. Our conclusion might seem a little bit sad. We'll just say, we simply did not have enough significant statistical evidence to support this claim, whatever it happened to be. Excuse me, wrong thing. Let me just start over. We do not have enough significant statistical evidence to support this claim in the alternative hypothesis, is the conclusion we will give. So, assuming the null hypothesis is true, it's going to give us something we can use in the central limit theorem. We'll use a normal distribution to get out p-value, and that's where we're going to find evidence for the alternative hypothesis. So there's lots to think about and write down when we're doing a hypothesis test. But any questions at all, folks, with the initial definitions and the analogy? Okay, well, let's move into this phase here, analyzing alternative hypotheses and a null hypothesis. This is like the first phase in hypothesis testing. If you can determine what the population parameter is in the very first place, you're all set. The procedure moves pretty quickly. But you might have also noticed there are two parameters on the table for us that we're thinking about. So let's put down a quick table. So if our data happens to be, say, quantitative, let me fix the table. That's a bigger word than I expected. Or if it happens to be categorical, that will absolutely affect which parameter we're going for. So the parameter, same parameter when it's mentioning population parameter, these 4 different times. For quantitative, it'll be mu. If we're looking into bigger statistical analyses, there might be multiple parameters mu that we described, but first in chapters 14 and 17, there'll be just one. Likewise, if the data is categorical, the parameter will be lowercase p, population proportionate successes. We haven't done a lot with categorical data just yet, just a couple problems here and there, but we will be returning to it really strongly in chapter 19. But first, keep in mind, that's what we mean by population parameter. We're either describing a mu, we'll be doing mu in chapters 14 and 17, or lowercase p for population parameter. Next is hypothesized value. That's something that comes from the problem itself. Sometimes the hypothesized value is, say, a national value, or maybe it's a value that you saw historically, like the 2 becquerels per kilogram would have been a hypothesized value. Something from the context of the problem is going to give us that hypothesized value. But notice that part right there is duplicated 4 different times as well. So we'll have hypothesized value on all the 4 statements. So the null hypothesis we only write down once, and the alternative hypothesis we only write down once as well. So it's kind of annoying that there's 3 different versions. The context is going to tell us which version we actually do in our problem. And they all have names, so we might as well name these. If you see a greater than, we're looking for evidence that the parameter is larger than some hypothesized value. Like in the last problem, the baseline level for radioactivity of Pacific bluefin tuna was 2 becquerels per kilogram. We could have been looking for evidence that our population mean mu is greater than 2 becquerels. We'd call this one a right-tailed test. Likewise, in a different scenario, if we're looking in just one specific direction, less than, we call this one the left-tailed test. And this test is extremely special in the sense that it is the default. If there is nothing in the context of the problem that indicates a specific directionality of greater than or less than, we're testing in both directions, and so this one is called the 2-tailed test. And it's considered the default. It's the default in the sense that if we see nothing in the context of the problem that specifically states a directionality, we will always be using this test right here. And so it's part of our job to determine what is the parameter. We have to write it down cleanly and very precisely. We then have to decide what is the hypothesized value, so that will get a null hypothesis, H naught. Then we have to decide what are we testing for. Is it going to be a right tail, left tail, or 2-tail test? After we've done all of that setup, the rest of the problem is not too bad. This is the hard part, getting over the hump with hypothesis testing so far. And by the way, if you're taking the biometry lab, there's one massive point of confusion. Our particular author will only ever use equality in the reading of this book. But in biometry, you might have gone this way. Let me use maybe this color. Another format could be H naught. Let's just focus on a specific parameter mu equals mu naught, the value to be tested. If that's our null hypothesis, our alternative might be HA, mu is not equal to mu naught. Or in a different scenario, we might have H naught, mu is less than or equal to mu naught. That means our alternative hypothesis is that mu is strictly greater than mu naught. Or other format is H naught, mu is greater than or equal to a mu naught value. In this case, the alternative hypothesis is that mu is less than mu naught. So this is how the biometry lab does it. Our textbook only ever uses equality in the null hypothesis. So it puts me in kind of a weird position where I'm going to accept a lot of different versions of this. So if you want to do it the biometry lab way, that's completely reasonable. That's possibly how you've been practicing that already in that lab. If you're following the book more closely, you might only be using direct equality, and that's perfectly reasonable as well. I'll be following the book, so I'll often be using just direct equality, but occasionally I'll make a comment like this, or you could have said the null was, say, less than or equals or greater than or equals. But notice the major thing about the null hypothesis. There is always an equality somewhere, either a direct equality, less than or equals here, greater than or equals here. So always equality in the null. And the alternative hypothesis never has an equality in any format, no matter how we write out a result. There's so much to say about hypothesis testing, but I think that's a good statement to make as well. Let's put it down. HA never use equality. And for the null, equality must be present. Maybe in the form greater than or equals, for an example. So with this big page of material and all the notes that we put on it, any questions at the moment so far? Okay, well, let me tell you how the notes are going to go. I want to do a couple scenarios of nothing but setting up hypotheses, because sometimes that feels like it's the trickiest thing about the whole procedure. So we'll do one where the context is really, really short, just to laser focus on how this goes. And then we'll do one where the context is more realistic. This is data that we've seen before. Finally, we'll state the whole procedure, where we'll show how to get p-values depending on the alternative hypothesis type of test. We'll revisit what conclusions can you even make and how you make them, which will cause a discussion about the significance level alpha. Then finally, we'll put this into practice on this problem here, ending with another concept problem, just like with the confidence intervals. So that's going to be the progression of the notes. But let's see if we have time to get through example 5. Just setting up the hypotheses is a hurdle in and of itself. Once you get past the hypothesis setup, the rest of it is not so bad. So it says for each following situations, define the unknown parameter, whatever it happens to be, using the context, and write the null and alternative hypothesis. Now, again, finding the parameter is tricky because you have to now think of what is your data? Is it quantitative or is it categorical? So here's our scenario. It says seatbelt compliance in Massachusetts was 65% in 2008. That's already a long time ago. The state wants to know if this has changed. But what's our data? 65% successes, being compliant with seatbelts. That's not quantitative at all. Quantitative needs to have a unit other than a percentage, for example. It needs to have something in terms of where an average might make sense. There's no average here. It's just a proportion written as a percent. So this is a dead giveaway alone that the data is categorical. You have to be pretty careful with that because percentages don't guarantee it's categorical. You might have a whole bunch of percentages and you're taking the average of those, analyzing an average. So the best determination is quantitative is going to make sense if averages are part of the question, something that we're going to analyze in the problem. If there are no averages and no units whatsoever, just a percentage, we are absolutely looking at categorical, like in this problem. It then tells us our parameter is P, population proportion of successes. So we can write down that P is going to be equal to, the state wants to know if it has changed. So we're thinking currently, say 2026 in February 11th, P equals the population proportion all drivers in Massachusetts, I'm realizing I don't know how to spell that word too well, Massachusetts, there we go, that are currently seat belt compliant. So that's our unknown parameter P. We don't know what that value is currently. We just know the historical value, 0.65. That's the hypothesized value that we're going to test in the problem. So the moment we find this 0.65, running out of colors here, let me go like this. This is P naught. We want to write it as a decimal just so that we don't get mixed up in our formulas, but if you left it as percentage in the hypotheses, it wouldn't be that big of a deal, just a unit change really. But once we have the parameter P down, here's how we can write out our hypotheses. We will test H naught, that P equals, against, leave a little bit of space after the equality, HA. We put a colon here because we're not saying HA equals, we're just saying HA is a statement that we put down on the right. We'll put P and something. And the next thing we put down is the hypothesized value. Notice it goes everywhere, whatever your alternative is and whatever your null is. So we put the parameter in those two locations, both here and here. It doesn't hurt to highlight that a little bit. There's the parameter. We put the hypothesized value in both spots, 0.65. Put a little bit of space on the alternative, 0.65. And now all we need to do to finalize this is find out if there's a direction. You know, it could have said the state wants to know if it has gone down. Maybe they had a bunch of, say, public service announcements that they've been blitzing as a campaign in 2025, and they want to know if people are, rather, gone up, are more compliant, more likely to buckle up because of that campaign. That would have been a right tail test, a greater than. But it just says they want to know if it has changed. That's no direction at all. That means this is a two-tail test. And so our alternative hypothesis has to look like that, not equals. We're testing in both directions. Well, that's the setup of hypothesis testing so far. This is the statement to be tested. It's a statement that nothing has changed since 2008. In 2026, they're still 65% compliant. The drivers are exactly the same. A null hypothesis is always a statement of no change in the population. Everything is just as it was. But this is the research question. That's what we're trying to find evidence for, and that's encapsulated in the alternative hypothesis. So a good way to think about both these things in hypothesis testing is the null is a statement of no change, and the alternative is a statement of the research question. They put a question here with a question mark, but the research question is, has seat belt compliance changed in Massachusetts currently, say 2026? That's the research question, and it's encapsulated here. In fact, if you were to just read this out left to right in the symbols, you would say P not equal to 0.65. But a better way to say it is, we are testing if the population proportion of all drivers in Massachusetts that are currently seatbelt compliant has changed from the historical value of 65% or 0.65. So that's hypothesis testing in a nutshell, and this is basically the hardest step. Define the parameter very clearly, stating both a null and an alternative in terms of that parameter value. Any questions or comments at all, folks, getting through this one? Okay, well, we've got 5 minutes, and I bet if I talk fast enough, we can do part B just in time, but I won't do that to you today. This one's a good one to break down, take our time with it. And then when we come back a little bit fresh, not on Monday, we have President's Day coming up. When we come back fresh, a week away from today on the 18th, we'll revisit this, start off fresh and see how it goes on that very next problem before we get into our full method. But if you don't have any questions, folks, have a nice weekend. I'll try to get these exams graded as soon as possible. I'm hoping for Friday early, but it'll be Sunday evening at the very, very latest if anything goes wrong. Have a great weekend. Have a great holiday, folks, and I'll see you all Wednesday.